Hello students, welcome to EPG Pathshala. I am Dr. Amarjit Singh from Himachal Pradesh University, Shimla. Today we are going to discuss about a module crystal defects, especially point defects in this module from paper solid state physics. So students, let's see what we are going to learn in this module. So when there are defects, we know that there can be defects in various way. So we are going to classify this defects, point defects, and also trying to understand from the point of view of thermodynamics that how it is not possible to get defect free system at room temperature or at any finite temperature. And we will understand the geometric patterns of different defects, and then we will slightly discuss about alloys and solid solutions. You might have heard about liquid solutions, but what are alloys and solid solutions? Because these are comes under also the category of defects, because when we say alloy, it means material is not pure, and then there are defects in the system. And so the whole idea is to understand how defects are useful for giving us a material of desired nature and property we want. And actually these defects are desired, we will see, and that allows us to use a material in a different varied ways. It changes its properties, physical properties, optical properties, electronic properties, etc. So how to define a crystal defects? So first let me make a statement. A perfect crystal is an idealization. There is no such thing in nature as perfect crystal. Atomic arrangements in real materials do not follow perfect crystalline pattern, though in theory it is such, and it appears like that, but you can see that you can purify certain crystal to certain extent, and there would be some impurities even when you use very standard, very high advanced synthesis method of the crystalline systems. Also, we will learn that there is a thermodynamic principle which does not allow us to have a defect free system, and we will definitely have a defect at a given temperature. So here we are going to categorize defects in terms of different dimensions, like zero dimension. Zero dimension is called because when, let us say, one or two atom is missing from some places, you call it zero dimension in a theoretical sense. And there are line defects. Suppose this defect is along certain line, and then two-dimensional defects, like if the defect is there in the plane, and three-dimensional defect is if it is a void or big kind of defect is there. So these are the type of defects we are going to discuss. Point defects. So here we are going to talk about the point defects, and in this slide we have diagrammatically tried to portray diagrammatically what a vacancy in a lattice would look like. As you can see that this is a set of ordered lattice, but somewhere in the middle, as shown by arrow, some atom is missing, and due to this missing atom, you can see that there is slightly a distortion of this plane in the vicinity or the locality of this particular type of vacancy. So when you have such type of a defect, that is called point defect. So it is like you removed a point from there. So that's what it is a point defect, because you're removing one atom from a particular point, and that makes it a vacancy. Now this vacancy will have its consequences on many of its physical properties. It can have influence on optical properties, it can have influence on electrical properties, and so on. So those we shall discuss separately. So you can see in this diagram, this is the real imaging of a sample. Earlier in the earlier slide, we have seen this vacancy in terms of a model. We prepared a model and then we defined a vacancy. But in this diagram, there is a measurement on a surface of some particular sample, and you can see that there are black spaces which shows the absence of atom, and this white shows the presence of atoms. We can also see that these atoms are arranged in a hexagon pattern, and we have drawn here uh, a unit cells also. We can draw the unit cell connecting this the black centers like this. So this can form a unit cell. But what we want to point out here is that you can see an arrow in between this unit cell, and there is one atom missing here, and you can see that due to that missing atom there is some distortion around in the structure. So this picture is taken by this scanning electron microscope. So these defects can actually be now probed at the atomic scale. I mean, you can see that scale bar at this slide, and this is 10 angstrom. So naturally at 1 nanometer length scale, you can really see, or even less than that, that some point defects become visible at such a small length scale. Now you can see that in this slide the defect is of another type, though this is also a point defect, and you can see that there is an extra atom in the interstitial space. This is what is called interstitial space. So space between atoms which is lying empty is what we refer to as interstitial space. But you somehow, if you push some extra atom in between, though there is not a sufficient space for that atom to be there, so definitely it will distort again the nearby atoms and the atomic arrangement, and that is seen by these lines which is showing this that there is a distortion or strain trapped in this area. So this kind of point defects are called self interstitials, and this will have its own effect once again on its many physical properties. Concentration of defects. Now let me tell you that when we have a real crystalline substance, it is never perfectly ordered. In this slide, this is shown here that thermodynamically it is not possible to have a perfect crystal. You always have some vacancies or interstitials or some other kind of defects lying in the solids. So this formula is telling us NV, which is number of defects divided by N. These are the number of potential defect sites. So this number of potential defect sites is basically the number of atoms in a given specimen, because any atoms can be missing. So these are the number of potential defect sites. It means the number of atoms, and is equal to exponential QV upon KBT. This QV is an activation energy, T is an absolute temperature, and K is a Boltzmann constant. Now this activation energy is important. This tells us that how much energy is required to create a defect, a particular defect, and this temperature provides that energy. So as we know that we always are working with some finite temperature, room temperature, or even below that there is a finite temperature. So there is this exponential factor which contributes to creation of some defects, and just because there is a finite temperature, there will be thermodynamic concentration of defects in each kind of crystals and solids. So the ideal situation when we say perfect crystal, that is not possible. We always have some concentration of defects in a given pure crystalline lattice, and that can be determined using this formula. So on this slide we have shown a graph of nd upon n and t. So this is an exponential variation, as you can see, and qd here is a defect activation energy. So when you plot it on a log scale, so you see that it becomes linear with respect to 1 upon t. If you that's called Arrhenius plot. So from this plot it is visible that the slope of this plot is minus qd upon k, Boltzmann constant. It tells us that if with respect to temperature we can know nd upon n, it means we already know the concentration of defects by some method, by some macroscopic method or some other experimental method. We can calculate or know the activation energy of a defect, or vice versa. I mean, if you know the activation energy of this system, you can calculate the concentration of a defect at a given temperature. So in this slide there is an example for copper where we have calculated the defect concentration at a given temperature. So what you need is what is given, that the density of copper is, and activation energy of copper qd 0.9 electron volt per atom, and atomic mass, Avogadro number. From this we can actually calculate that how many atoms will be there in a given amount of sample or a given volume. So when we are calculating this, first we have to know that how many atoms we are talking about, how much is the total sample. So that gives us the value of n, and putting the value of k, which is a constant, we know, and also we know at what temperature we are calculating, and qd, it comes about to be we find out the concentration, and the concentration comes to be of the order of 10 raised to the power 25 vacancies. So the total number of atoms is 10 raised to the power 28 atoms. So out of which 10 raised to the power 25 vacancies will be there at 1273 Kelvin. You mean in 10,000 atoms there will be one vacancy. So you can see that if the temperature is low and room temperature, the concentration of vacancies will be quite low. So here in this slide we can see that this point defects we can again classify, and this is usually of two types. You can see that this is a crystal where you have two different kind of atoms, for example NaCl, and let us say one of the ion is missing from there, some cationic vacancy is there on the left hand side, and you put it at infinity or take out of the sample. So this type of defect is called Frankel defect. On the other hand, on the right side, if you see that there is an red atom missing and there is a blue atom missing, so they are missing in a pair. So this kind of defect, when they are missing in a pair, is called as Schottky defect, and both type will have their different activation energy. So there is a QFR for Frankel defect and QS for the Schottky type of defect, and using their respective formulas we can calculate the defect concentration. So in this slide I will give you one very realistic and important example, and this slide will tell you why the study of defect is so important. You already know about silicon, which is a semiconductor, but if it is pure silicon, this is not of much use in the semiconductor industry. But if you dope it with some dopant, some atoms, some different atoms from silicon, uh, it becomes a very useful semiconductor that you call it either p-type or n-type, depending on what kind of doping you have done. So and that changes its electrical and optical and many properties so drastically. And to make them really working, we see that either we make them p-type semiconductor or n-type semiconductor. So p-type and n-type semiconductors are nothing but some sort of uh, materials with defects. So that is why the study of defects in solid state physics or material is so important. So let us see here one example. You see that A, there is a cubic structure here, and there are 4 silicon atoms at the corner and 1 in the middle. So if you remove this 1 silicon from the middle and insert an boron atom from there, so just because boron atom will have deficiency of an electron, I mean the total valency of boron is 3, so it will have just 3 electron where silicon had 4. So now there is one deficiency of electron, which you can see in diagram B, that one deficiency is shown. So basically there is a extra electron required there, or this is called hole here. So you have created a specimen of different electrical nature. You see, in place of B, rather you inserted a different kind of atom, that is P. So it has a valency of 5. So when it has a valency of 5, its 4 electrons will bond with nearby silicon atoms or satisfy the valency, but there is one extra electron which is shown outside. So this extra electron is basically a free. It is not wanted or required for the bonding. So this free electron will provide an extra conduction for this kind of material. So just like this electron can move, the hole can also move in boron, and then the conductivity of the sample can be enhanced just by doping some impurity materials in the pure semiconductor. So this was to illustrate that how defects and impurities are important in solid state physics, in the applications of solid state physics. In this slide, we have we will just mention in brief that how you can produce the defects, as we know that producing the defects in solids are quite important. So there are several ways where how we can produce defects in the solids. So it can be done during growth and synthesis. Impurities may be added to the material during the synthesis. Another way is thermal and thermochemical treatments and other stimuli. Heating to higher temperature and quench. So what this does, heating to higher temperature and quench, so that you raise the sample, you raise the temperature of the specimen. So as we learned in earlier slide, that higher the temperature, higher the vacancies, thermodynamic vacancies you create, and then you quench it. Quench is a term which is used that you suddenly cool it. You don't let it be cooled slowly so that atom can readjust, defects can readjust in their position, but they are arrested now in their position, and this defects remains always in the samples because they need a certain relaxation time which was not available because we quenched it fast, and now those vacancies or those defects will remain trapped in the specimen. So you can heat it in some reactive atmosphere, so you can have some gases and you can heat it and they can chemically react, and that way some impurities can be introduced in the sample. And heating in vacuum, like if you heat in vacuum, it can lead to the loss of oxygen if there is oxygen in your sample, and that means it will create some sort of deficiency of oxygen in the sample, or you can say this is another type of way of creating a defect. And the you can do it by deformation. Let us say if you apply some sort of deformation, that may also lead to slipping of planes. It can twist and remove some atoms and actually can misalign the orientations. So those things can happen. And another well-known technique is an ion implantation and radiation. So in this technique, you have a sample, you irradiate it with a high energetic beam of particles. So these particles will go inside the specimen, and because these are energetic particles, they will knock out many of the atoms from the samples, and that way they will create a vacancies and defects inside the crystal. When we are talking about defects and impure solids, we know that uh, alloys are basically not pure substance, but a, a, a impure materials. These are the impure materials. So those alloy are a class of impure materials that I'm going to discuss a bit, so that we understand that these are also materials with defects and impurities. So there are generally two types of alloying. The substitutional, the name substitutional of this solid solution tells us exactly what happens as atoms of the parental metal are replaced or substituted by atoms of the alloying metal. As you can see in the diagram, that these gray atoms are removed and some other atoms of the same size or nearly of the same character are replaced there. So that form a substitutional uh, alloy. So from there you remove one type of atom and you put another type of atom, and let us say it is a metal. And there are some interstitial solid solutions or alloys, as you can see on the right side, that it in between the bigger atoms there is an empty space, and in that empty space the smaller atoms can fit and they can come into the interstitial. So if there is this kind of alloying, we call it interstitial solid solutions. So that is two different kind of solid solutions we can make for different purposes. We are talking about defects and impurities in the system. So alloy is one such system which we can call impure, because you prepare an alloy by mixing a different type of uh, material, or let us say metal, with another metal. So the question is how to make a good alloy where um, the one component is going well with the another one, or it is not segregating into different phases. So for that, the important one of the important thing is the structure factor, that both of the compound should have almost same identical crystal structure factor. So if you mix these two such solids or metals, you are likely to have a perfect alloy. Example is copper and nickel. So they have both same crystal structure and almost same atomic size, and if you mix them they form a very nice alloy. So another uh, thing is the electronegativity. The more electropositive one element and the more electronegative the other, the greater is the likelihood that they will form an intermetallic compound instead of substitutional solid solutions. So when we are saying alloy, it should be a kind of solid solutions where one atom is behaving just as it is an atom of parent um, material, so that it should we say gel well, or bond uh, uh, exactly replaces the atoms which is already present there. So this was about an alloy. So students, let us summarize what we have learned in this module. uh, First of all, we learned that in practice a perfect crystal does not exist. We always have defect which is predicted by thermodynamics, or with the help of thermodynamics we can predict the concentration of defect at any finite temperature. Presence of various type of defects result in different physical properties. uh, for example, optical, mechanical and electrical properties can be drastically modified. A point defect can be several types, such as vacancy, interstitial, impurity atoms, etc. And we learned that alloy is a solid solution of substitutional of substitutional type or interstitial type. So there can be two types of alloys which are um, useful in making a solid solution, a perfect solid solution. Uh, we see that the subject of this study of defects is very important in solid state physics. Indeed, if you see that our whole semiconductor industry, we use diodes, transistors and all, these are all impure material with the defects. You call some as a p-type semiconductor, another as a n-type semiconductor, and you know that these are the systems with the defect. Either it's a substitutional or interstitial. So you basically remove some atoms from some position and implant another atom over there, creating some sort of defects and creating a beautiful devices. So this was to highlight the importance of defects in solid state physics. Thank you.